where when we talk about descriptive statistics, please understand it just gives a description about what you call what the data we have. Again, I'm reminding you, descriptive statistics will not satisfy the hypothesis testing or verification of the research problem. So descriptive statistics to be kept as descriptive statistics only. But it is very important because without descriptive statistics, we cannot move ahead. When you talk about descriptive statistics, it describes your data in different ways. That's the idea. Uh, Within few indices, and what are those indices? Because descriptive statistics itself is a big world of statistics, and you may not be knowing the amount of descriptive statistics where you can use it for explaining or describing your data in different ways. So you give a glimpse of your sample through various forms. That means you describe your data. So these are the ways you can describe your data, starting with the graphical presentations. Then you can describe your data through measures of central tendency. Then even through measures of variability. You can go for measures of relationship. I'm adding it here. Then you can convert the scores and still they are called as descriptive statistics. For example, STEN scores, STEN9 scores, T scores, and Z scores. We'll be discussing all. We start with the first one as a graphical representation. So many times we represent data through pictures or graphical presentations, and a lot of softwares available to make your graphs. For example, there is a graph pad is available. Microsoft Excel is one of the what you call prominent and popular sheet to generate graphs. But whatever it may be, uh, you represent the data through a picture or pictorial way where it gives the distribution a glimpse of it, what exactly it looks like. But if you go back to the history of it, it is William Playfair, okay, as back as 18th century. He is the first principal inventor of statistical graphs. In 1786, he publishes a article called as Commercial and Political Atlas, which had 44 charts. Of the several charts available, he invented three of the four forms of graphs. There's a line graph, bar graph, and a pie graph. These are the things where he planned as back as 17th to 18th century. What exactly what you call graphical representation as a descriptive statistics provide us the details. Now remember, many times looking into the article numbers may be boring, but if you present the data through pictures, I think it gives a better result, which can be seen during our election analysis, during cricket matches, where the data is being represented more by graphics than by numbers. So the graphics gives a quick idea. So and it gives what you call a overall picture in a nutshell. So that's the idea. It can give you on the trends. So that is where graphical representation is more attractive, and it gives a good visual display. That's the idea. And in research also, what I call academic and professional disciplines, it's used, and in mathematics too, and all the most of the sciences, the graphical representations are quite common. So the idea is even a common man can understand what are your results are. So that's the idea. It's not only just for a researcher, anybody can understand. If you show the pictorial representation of your data, then it makes a better sense for them, which makes the idea very simple. So that's the idea. There are different types of graphical displays, and if you see the what you call graphical displays, it can be bar diagram, it could be column diagram, it could be histogram. So there is a spelling mistake, just correct it as histogram. So we'll see individual each of them. Then there will be frequency polygon or line diagram, and there could be cumulative frequency graph or OGI. There could be a pie chart, there could be scatter diagram, pictograms, area graphs, and there are other types. So a series of graphical displays can represent your data through the graphical displays, we'll look into one by one, and most of them you are very familiar with, but anyway, we'll follow some rules and I will check. So a bar diagram, when you talk about a bar diagram, please understand the idea here is you are representing your data in terms of rectangles positioned in a specific way. It can be used for a mean value, it can be used for the minimum nominal data, or it can be ordinal data. So whatever it may be, the idea is you have to make a graph. But remember, when you talk about a graph, you have x-axis and y-axis. And remember, there you have to follow some rules. Sometimes you see a full page of what you call graph, but it's not a good graph. A good graph should follow what you call a standard condition of rule. For example, if x-axis is what you call 100%, your y-axis should not cross more than 75%. So that is a rule, and in extreme cases, it can be 60 to 90%, but it cannot be exactly as what you call length as y-axis. So the height of y-axis should be approximately around 75%, with the range of 15% each. Can go till 60 to 90% of x, but definitely not less than that, 60 or not more than 90, because then the symmetry of the graph would go. So these are the few of the simple rules you have to follow while forming the graphs. I've seen in some of the thesis a full page graph where y-axis is double of x-axis, which is very unscientific in nature. So be careful while presenting the graphs. And again, I'm repeating, the rules are very simple. Your height of the y-axis should be 75% of x. That's a standard rule. So keep in mind. And when you talk about a bar diagram, there could be, you can present the data in one variable, or you can present the data in more than one variable. So if you present only one variable, then it's called a simple bar diagram. And if you're presenting two, then it's called as a compound diagram. So these are the various ways where you can display your results. So here, if you see what you call the graphs, the first one is called a simple one, where the data is shown either vertical or horizontal way. So you can see, or there could be a compound graphs where two variables are shown together, or there could be a what you call a graph which called as a cluster, where you can see one graph placed over the other graph, so that you can see the relative change in the variable over the time period or over a specific x variable against y variable. So you can see the changes. If you see what are the changes happening, so your bar diagram could be either simple or it could be a compound diagram. But the idea in compound diagram is you save your time, you save your this one uh, time as well as space if you use compound. Otherwise you have to have individually you have to show, that it will be many graphs. And when you show a compound graph, indirectly it gives the idea of comparison between two variables on for a particular issue. So a compound graph will give the better idea than a simple graph. So this is a way you can represent the bar diagrams or bar charts. Then frequency polygon or line diagram. Remember, here what is going to happen is we are showing through a continuity. Remember, when you talk about a frequency polygon or line diagram, the variable should be a continuous one. So it could be what you call this one, what you call a temperature increase or decrease over a period of time. So this can be used on a what you call a line graph rather than what you call bar diagram, because in bar diagram we usually see the discrete categories, whereas in line diagram or in frequency polygon we can see a continuity, because you join two points by mere straight lines, connect one to one, so that there will be a beginning and there will be an end. So you connect the data points, and what is, you can see easily the trend, what is happening. So you get what you call visualize a trend in data over intervals of a time series. So usually it could be a chronological one. And again, as we've seen in what you call in the bar diagram, it could be simple line or it could be compound diagram. So either one of them we are going to use, simple or compound diagram. So accordingly, they look like this. If you have seen how a simple diagram would look like, and it will be looking in the other direction, where if you see here in the first graph, in the simple, you have seen only one variable over the years is shown, whereas here the further data is bifurcated into three levels, so that three different independent variables have been shown or through over the time period, three different lines. So now the comparisons would be much easier. So that's the idea, wherein you can see simple and compound diagrams. A simple diagram basically you show one graph at one line at a time, whereas in compound line you can show several lines. But the idea here is in compound diagram you can get a comparison which is more or which is less. So that's the idea. Then we have cumulative percentage graph, and technically called as Wagai. So now, okay, anyway, I'm not going to tell the procedure how it is been done. You can see in the book or learn through YouTube videos. So once you formulate the OGAI, the advantage of OGAI is you can calculate different percentile points. That's the idea. So when you talk about different percentile points, as we discussed, it can be 70th percentile, it can be 50th percentile or 20th percentile or any percentile point. Now remember what you have done in cumulative percentage graph. We have converted, first we have taken accumulation of individual points cumulated over the class intervals or intervals, then converted them into percentage. So if you see the end point, if you see the highlighted version here, it is only 100. So now you can cut point here with anyone. Suppose you want to cut 25th, you have to cut here and you draw a slope down. So cut here to the line and draw a slope down. Cut here, and you can get each point in the x-axis as 25th, 50th or 75th percentile. You don't require any statistical calculation. You can through what you call through OGAI or cumulative frequency percentage graph, you can directly calculate any percentile point, any quartile point with much ease. So that is the idea. So you can easily do that. Then comes pie chart. Pie chart also representative, but again, as you've seen, it is used for a discrete category. And again, it will be used for a nominal or ordinal variable. Usually we don't represent mean values in a pie chart. Mean values are not a good way of representing the what you call data through a pie chart. For them, we have to use a different graph like line graph or bar diagram. But the idea in pie chart is you divide the what you call entire circle, because now the entire pie chart is shown through a circle, and we are going by the property of a circle where we try to cut down the angles according to the frequency or number of occurrences, and everything is converted into angles because we proportionately share it to 360 degrees. So once you do that, your pie chart would be complete. So what exactly it's going to be like? It's a 360-degree presentation, and you can compare subclasses of categories to the whole class or categories using differently colored or patterned segments. So I'll show you that. So as I said, it is to be drawn to depict or show the total volume of the given attribute or given a variable. You can use a circle, divide a circle into corresponding degrees of angles, then represent the subsets of data. So sometimes it's also called as divided circle diagram, but most familiarly it is known as a pie chart. So how they look like? There are different kinds of charts. See, one is a plain one. If you see the first one, it's a plain pie. Whereas in Excel, you can go for a 3D pie where you can see the depth. So there is a third dimension which is added here, not only length and width. This could be there's the depth also. There could be donut where you can find a hole in between. But remember, chart whenever you make a pie chart, if there are too many categories, it's not advisable. If 3 to 4 categories, it's good. But if there are too many categories, deciphering what is what will be difficult. But in Excel, you can make this very easily. But this also represent which color is more dominant and what exactly each, say for example, now January is very less, whereas compared to May is very high. Now all this will give us idea, some trend regarding the data part. So whether it could be simple pi, 3D pi, or donut. So there are ways we can manage. Then you get a scattergram, which is more what you call used for us in scientific research. When we say scatter diagram, understand it's going for a pair of scores. So how the pair of scores would come is you have two pairs of scores, one is x and one is y. Against each x, you are going to plot the value on the x y axis, so that several such points will be made as a dotted each dot will be made, and the dots will be called as scatters. So based on that, the scatters are seen. For example, you can see here, for example, here you have some what you call for each x value, last this one, and what is happening to, for example, uh, cow milk production or cell counts. If you want to what you call relate it to last month to this month, over the what you call months, you can see over the last months against the this month, you can see the blue color is increasing, whereas if you see red is somewhat spread. So the idea here is each x against each y will be a single dot, and this will be called as what you call cluster. Now, if you see in the down, I made a very specific one where you have got x and y, where you can see against each x you have one y variable, so that there are several variables have been put. And the advantage of this in scattergram is you can go for a simple fit. Now, if you see a dark but thin what you call black line which shows the trend of the data. Now that's the idea. Through scattergram, you get to know the trend of data, and by that you can calculate a regression equation. So the regression equation, which we will be discussing tomorrow or maybe today, we'll see, which helps us to predict. So with the scattergram, it's not only you're just plotting the data x against y, but you are also getting what you call a trend line, which can give the trend of the data, so that the prediction would be easier for the future, where you can easily point out this could be the possible change would happen in the subsequent year or subsequent quarter, or whatever the timeline you want to keep. So that way you can go for a scattergram. Then comes pictograms. Okay, that also representation of graphics in research, but as such we don't use much of pictograms in research. But these are the pictograms are typically used in what you call in representation of data. So if you see, there are by looking at what you call the each picture only, you can get a meaning out of it. So this because one need not explain, one can just looking into the picture what you call it's a kind of a icon or ideogram, because it is a pictorial resemblance to a physical object. I think nowadays you are more into emojis. I don't know how many of you know. I think you must be using a lot of emojis, but this is much more than emojis, because when you talk about emojis, they are basically expression of emotions, and that's why they are called as emoticons. So when you talk about emoticons, they are very specific. But here you can find all related to human beings. A different what you call picture will give a different idea, and one doesn't need much of explanation. So that's where pictograms are useful. But as I said earlier, may not be used much in research. Then comes area graph, maybe in geography and all. I think this could be what you call much easier. Now you see group ABCD have been displayed through different areas in what you call with the different colors, and each area, if you see how much coverage it comes. For example, over the day something is been given. So variable x and y, the one is the timeline 1, 8, 15, 20, 29. Whole of January is being covered, and some specific variable is being described through a picture, but each one comes through what you call a color. If you see, this is the area covered by what you call group A, this is group B, group C, and group D. So each area has got a specific meaning, and you can compare each area coverage with the other coverage. So that's where area graph can be useful. Then you have what you call box plots, maybe not much used in social science, but definitely you can also still use a box plots. Basically gives the idea into second and third quartiles, and you see a vertical line inside the box. Now if you see what you call some of the journals, you must have seen like this. Now what exactly the meaning of that is, we can look into the next one, next chart. Now you can get to the box plot details. Now see, this is what exactly a box plot says. You have a what you call, you have a rectangle, and a line is what you call drawn up with the cut and drawn down, and the lowermost value is called as minimum value in the data set, and topmost value is called as maximum. In between you have got two boxes, that's the first quartile and third quartile, nothing but 25th and 75th percentile. And in between, and the first and third quartile amounts to IQR, interquartile range, and in that if you find another line called as median line. So the median line, which gives idea of the exact 50th point in a distribution, that means 50% of the cases above and 50% of the cases below. So this is where in one chart you can display so many things which cannot be done through a regular mode. So box plot also very much useful, apart from scatter plots and other types of diagrams. All these are used in research. So box plots gives a lot of idea. So this is where we are talking about the different types of graphs. But remember, whatever it is said, graphs are still not be 100% representative of the original data. So that's the idea. Still, graphs are graphs. Nothing can beat the original data or your analysis. Graphs are just supplementary to make it more what you call neat and get a quick trend out of it. So that's the idea in the graph. So the next one, so graphical representation as one of the measures of descriptive statistics. We'll move on to the next level of what you call descriptive statistics, referred as measures of central tendencies. So once we talk about measures of central tendencies, the idea is they are also called as measures of central locations, also called as measures of averages. They go by different names. So the purpose behind them is to find out a single score which represents the entire set of scores. Suppose you have got several scores in your data, raw scores, and you try to pool them and divide by that many number, you will get a mean. So you get a single score from the entire set of data, so which can represent as one of the data value which represents the entire set of scores. Then suppose you have got two such scores, you can compare between two scores. For example, a group of boys versus group of girls. Okay, their academic achievement. Now you can say on an average whether boys are going high academic achievement or girls have got higher academic achievement. On the basis of what you call mean or average, we can calculate that. So basically these measures, again I'm repeating, whether it's mean or whether it's median or mode or harmonic or geometric mean, they will represent a single score which represents the entire set of scores. Second thing is, suppose you have two such scores, you can compare between them. So the mean, median and mode are most commonly used measures of central tendency, if you remember, which have already been discussed. And suppose you want to go for a characters of good measure of central tendency. Now you can see that it should be based on all the observations, should not be affected by extreme values, should be as close as maximum number of observed values as possible, means cover all the values. Then there should be a rigid definition for it. Then even if you get a measure of central tendency, later you should be able to what you call go for a higher level and rigorous calculations. you should be able to do further algebraic treatments. Then whenever sampling fluctuation occurs, it should not change. That means what? The stability of mean is very important. So when you talk about measures of central tendency, usually we talk about mean, median, and mode. Adding two more, geometric mean and harmonic mean, you can add that also. But remember, those geometric mean or harmonic mean are not much used in research. They are used under specific conditions. So again, but for what you call, for your reference, these are the 5 types of means available. But usually we restrict it to mean and median. Even mode is what you call not used much in research. Mean and median are the 2 important things being used. So again, if you see arithmetic mean, I don't have to explain all this. It is you make a total and divide by number of items, you get a mean. Again, it depends whether you are using a group data or ungrouped data. You must have done from your childhood days or high school days. Then what are the advantages of a mean? If you go for a descriptive statistics as a mean, the first advantage itself is it's easy to understand and simple to calculate. You don't have to much worry. Add up them and divide by that many number, you get a mean. And in the frequency distribution, you take a midpoint and multiply by its corresponding what you call frequency, cumulate them and divide by sigma fx by n, you get a mean. So it's quite easy to understand and simple, and is based on all the values. This is more important. Mean considers all the values, whereas median and mode do not consider all the values. Then even if some of the details are lacking, still you can go for a what you call mean calculation, and it is not based on the position in the series. Like median and all, it's based on the exact center, but now this will not consider the position of a series, so it is much easier to calculate. So there are the advantages of mean. Then you have disadvantages. It is affected by extreme values. The meaning is says if one value is very outlier or very far from the center, so that can change the entire structure of the mean. So extreme means do have influence on the calculation of mean. Then whenever in frequency distribution, if there are open-ended intervals are there, then still you cannot calculate the mean. Mean cannot be located graphically, which is not easy. Sometimes mean can give misleading conclusions just because of extra scores or distinct scores might change the structure of the mean. Then it has upward bias too. That's also not good. So when there are upward biases are there, that will be a problem. So all these will have the disadvantages. Then go for a median as a second, what you call second measure of central tendency. So median is, as I said, it's an exactly central value. That means that if you calculate a median, 50% of the cases are above that point and 50% of the cases are below that point. So the idea here is, suppose you want to divide your entire sample into 2 groups, you can calculate a median and then divide into 2 equal halves by taking what you call median as a measure of central tendency. So suppose you want to make a high group and low group, or high achievers or low achievers. So in such cases, you can go for a median as a central of central tendency. So the what you call the calculation of median, I'm not going to talk much about it because you can always refer to the textbooks and later the PPT also, which will be shared with you later. Then what are the advantages of median if you look into? So median can be calculated for all the distributions, whether open-ended or closed-ended. You can calculate any type of distribution, you can calculate median, because median is not affected by extreme scores. That's the idea. And median can be understood by even a layman because you know it's exactly 50th point and you cut it and you get to know. And even the extreme items are what you call outliers are there, still median may not be changing. So your median is much safer than the mean. Then median can be located graphically. So easily to locate. Remember how we have gone for what you call Ogayo. If you remember Ogayo back in the morning, in the first session we did, that's where you exactly cut the what you call graph into 50th percent point and down the write down or draw down slope, and that point would become a median. So it can be easily located through a graph, and median is a good statistics when you deal with the qualitative data rather than quantitative data. So that's the idea. But disadvantages, because median will not consider the outside values, it considers only the central values. So it's not based on all the values. So that's a major disadvantage. Then once you calculate the median, you stop there. You don't go for further calculations. But with the mean, you can go for many calculations further. So that's the idea. But median, you stop at once. Then median is affected by fluctuation of sampling. If there is a sample fluctuations are there, the median also would change. So by our standard, this should not happen. So still it's a disadvantage. So in case of even number of values, it may not be the value from the data because it comes somewhere in between the average of 2. So in such cases, it's not a true value which is coming from the distribution. It's a new value. So that also can happen as a disadvantage. Then we have mode, or sometimes we refer it as model value. So once we say model value, try to understand it's designated by the letter Z. And the idea here is model value is the value which occurs most number of the times, or the value of the item in a series which repeated more number of times. So that's why it's called as model value. Or suppose you draw a graph or line graph or a bar diagram, the highest point which the series has, that will become a model value. So it's basically very simple statistics, and there are two types of modes. One is a crude mode and the one is a true mode. Crude mode is by visual display only, you are trying to calculate the mode, whereas in true mode you apply a formula and then you calculate the mode. So crude mode, as the name says, on by looking into the data only you can decipher what could be the mode, and in the case of true mode you apply a formula. So whatever it may be, again not much used in research, and this is the formula where you can think how to calculate, but we are not going to do that. Then the advantages of modes are, it's readily what you call comprehensible and easily calculated. Sometimes you don't even require a formula, you can directly look into the data and decide what could be the mode. And mode is the best representative of data because it shows which is really highest and which is really lowest. So that's the idea. And when the what you call, when you do this graphically, the data set is shown through graphically, the value of mode can be also determined graphically. That's the idea, you can easily identify. Then mode is usually actual value of an important part of the series, because definitely mode represents one of the values which occurs most number of the times. So it is one of the values in the existing data set which may not be there in the median or the mean. So that's where we are going to talk about the advantages. Disadvantages are, it's not based on all observations. Remember, whether it's median or mode, these two are not based on the what you call all the observations except the mean. Then once you calculate the mode, again you stop it there. You are not going to do further calculations. Then whenever there are sampling fluctuations are there, mode is highly affected. So sampling fluctuations do affect the mode. Then when you make a choice of the grouping, it has an important influence or great influence on the value of mode. So this also would be there. So that's where we talked about disadvantages of mode. Now you have seen three types of measures of central tendency: mean, median, and mode. So usually if you now go back and have a flashback, a mode is not used much in research. It's only mean and median, and within mean and median, mean is used more. Median is again used for specific calculations when you require two groupings, or when you think that extraneous variables do have significant influence. In such cases you go for a median. There are other two what you call types of means. There geometric mean and harmonic means are there. but we are not going to discuss about it because in social sciences hardly we use these two statistics like geometric mean and harmonic mean. Then when you talk about the measures of variability, the next set. So we have finished graphical presentation. We have finished measures of variability. Now we move on. Sorry, we finished measures of central tendency. Now on the third level, we move on to the measures of variability. Now remember, when you talk about the measures of variability, how it is different from measures of central tendency. In measures of central tendency, we saw how all the scores grouped together and end up in giving up a single score which represents the entire set of scores. Whereas in variability, we see how those individual scores are different from measures of central tendency, either mean or median. That means what? Measures of variability would measure the heterogeneity or the homogeneity of the data. Please have this in your mind because measures of variability has a great significant influence on your results because these measures of variabilities would indicate you whether your data is heterogeneous or homogeneous. So if your data is heterogeneous, take it for granted, you are bound to lose your significance in the inferential statistics. If your data is homogeneous, then you are bound to likely to get the significant values. So why? Because the moment the what you call the heterogeneity increases, it increases the variance. Once the variance is increased, automatically the test statistics value would be less, and automatically it will become non-significant. So that is why when you talk about the variability, you have to be very careful while collecting the data. So usually we say a variation in the data is the heart of statistics because that gives a complete what you call profiling of what you call nature of your data. If there is no variation, no need to statistical analysis because it's all variation is coming zero, then you don't have to do any furthermore statistics. Only the mean would describe the distribution. So that's the idea. So, but you will have some kind of variation. So that's where you have to be very what you call careful about your extent of variability of your data when you subject it to analysis. So what are the different methods if you see measuring variability? So the range is a very simplest but crude and quick measure of variability. Range is usually measured by highest minus lowest score in a distribution, and the problem here is it considers only the highest score and the lowest scores. It will not consider what you call any of the other details or any other scores in between. Next, you have got quartile deviation, where again not much used in research. QD is what you call, it's also called as a semi-interquartile range, where you can calculate first quartile and third quartile, take the difference, take the half of it, then it becomes what you call quartile deviation. But if you see mean deviation, that's the next one. Again, not much used in research, average deviation. But if you see standard deviation, this is where where we're talking about the heart of statistics. A standard deviation reveals a type of variability you have. If the standard deviation is high, that means your data variability is more. That means heterogeneity of the data is more. But if your SD value is less, that means you are into more homogeneous data. Now, when you talk about variance, now understand this variance. A variance is nothing but SD square, SD into SD. So that gives the extended version of variability. But suppose you see the standard error, you're seeing the standard error as one of the measure of variability. So some of the journals, they don't expect what you call standard error, sorry, standard deviation. Some of the journals insist on standard error rather than standard deviation. So what does the standard error indicates? By the formula, standard error is equal to SD divided by square root of n. So now this gives idea that is furthermore reduced measure of variability. So there is a saying, if SD gives the variability of the sample you have selected, Standard error gives the variability of the population from where it has come. So that means what? Automatically a population is large and the distribution is quite uniform. So automatically standard error would be lesser than standard deviation because you are dividing SD by square root of n. Then sometimes we use the word covariance, that also will be as one of the measures of variability. But remember, at least SD as one of the major methods of variability you have to take into consideration, otherwise it has a great impact on the analysis. Now when you say the what you call great impact on the analysis, why I'm telling, because when we say standard deviation as such, somebody's mic is on, please mute. Okay, now I'm coming to the standard deviation point, why it's important for research. Now try to understand one point where a standard deviation is high, it indicates that okay, there is a more heterogeneity, and more heterogeneity spoils your significance. Now why that heterogeneity has come? Since SD has come high, it gives the idea for you. Now that shows that either your sample selected is not a right sample for which you are selected for your study, or you have given a tool which is not appropriate for that age group. So because of these two things, your standard deviation may be high. So once the standard deviation is high, it indicates that your sample may not be uniform sample or a homogeneous sample. You may have given the what you call survey tool to a heterogeneous tool, heterogeneous population. That's why you have got a heterogeneous what you call data, which might spoil your analysis. So be careful about what you call the standard deviation part, because that's very important tool in measuring variance of your data or variability of your data, and it's represented by Greek letter sigma. So as I already discussed, it's a measure of dispersion of the scores around the mean, and the beauty of standard deviation is it considers all the deviations from the mean, whether it's a group data or ungrouped data. It considers even the individual scores for dispersion, how much it is far or how much it is nearby. So that's the idea where it considers all the scores into uh, for analysis. The higher SD indicates the dispersion is more, lower SD indicates your scores are together. So that's the idea. So already I've discussed about what you call the advantages. Very popular scientific measure of dispersion, because it takes the deviation from each mean to the other score. So that's why it's very popular. Weightage is given appropriately. Then once you have got a SD value, you can go furthermore calculation to skewness and correlation, etc. By these values, we can go for higher levels of statistical functioning. As I said, it considers all the items of the series. That's also more important. So these are the few things where you can talk about merit, but demerit is there's a calculation is slightly difficult compared to the regular deviations, because you have to have several steps to go ahead. That's one of the demerits. And whenever there are scores or outliers or extreme scores are there, they might increase the SD value, because the distance between that score and the mean is very lengthy. So automatically the more lengthy distance will lead to higher variability. So that is why extreme scores have got gained great importance in calculation of the standard deviation. Then quartile deviation as such we discussed. Okay, there are three quartiles. Q1 is 25th percentile. Then Q2 is a median or 50th, and Q3 is a 75th. So what we do is, as I said, it's called a semi-interquartile range, and how it will be calculated, like you have got Q3 Q1 divided by 2. So all the formula are given, but anyway, you can look into that later and find out. Then you got mean deviation, a reduced version of standard deviation, because in standard deviation, what we do is we take the score, we calculate the mean, take the deviation, then square the deviation, then apply the formula. But here we don't take what you call the squared deviations. We just keep the scores as such, but we ignore the signs. So that's where mean deviation works, because once the signs are ignored, everything looks plus, which could be in the drawback also. So this is a formula. We are not bothered about much of formula, but remember that is also as one of the measures of variability. Next comes the measures of variance. So this is nothing but it's a summary statistics indicating degree of variability among participants of a given variable. So basically it's a standard deviation is squared into twice. So SD into SD will give you variance. Okay, it gives a degree of variability, and if variability is high, you may have to have a second thought whether to recollect data or change the tool, or you may have to think of if SD is too much. So that's the idea, and variance can give a better idea how much is the spread of scores. Then standard error, as a in the introduction only I said, in statistics article, a sample mean deviates from the actual mean of a population, and this deviation is the standard error. Now, as I said, if standard deviation gives the variability of the sample which you have selected, the same variability can be extended to the population by using standard error. So you can use the formula standard error is equal to square root of SD by N. So with that, you can calculate the standard error. And as I said, few of the journals would rather require standard error than standard deviation. So that also is there. But remember, this is also one of the measures of variability as such. Then CV is equal to what you call the formula is sigma by mu. That's nothing but SD divided by the mean. So that also would be there. So once you have that, but not many people use the CV. Very few people will use the CV for measures of variability. But that also an index of measure of variability that we should remember. Then comes measures of relationship. Now we're on the fourth level. Remember, we started with the graphics. We went to measures of variability. We went to measures of central tendencies. Now we are going for measures of relationship. So when you talk about the measures of relationship, we go by two levels. One is a non-parametric form and one is a parametric form. In non-parametric form, we call it as a Spearman's row or Spearman's rank difference method. Whereas in parametrically, we are going to talk about Spearman's correlation or product moment correlation. So for non-parametric data, we have Spearman row for the rank data, and for quantitative data, we have got Pearson's R or Pearson's product moment correlation. So these are the the measures of relationship. What exactly are they? So correlations actually measure mutuality between two or more variables. That means what? It measures the dependence of one variable over the other variable. So that is expressed as a coefficient of correlation, and your coefficient of correlation can range from -1 to what you call +1, having 0 in between. That's where I want to show you. Okay, your correlation coefficient measurement can be like -1, can pass through 0 and may end up in +1. So when you talk about a minus, because your correlation cannot exceed more than 1, please try to understand this. If you are by calculation, if you have done a correlation and if it comes more than 1, that means there is a problem in the calculation. So you have done something wrong. So please don't do that. So once you have that in my mind, you have to be very careful. Your calculation is wrong. So the calculation, it has gone wrong because there could be some steps where you have missed. So what you can do is check again. because it cannot exceed 1 either side, on the minus side or on the plus side. So on the minus side it's minus 1.00, which is referred as a strong negative. And sometimes you may get a correlation as 0, that means no relationship at all. And sometimes you get plus, it's a strong positive one. So your correlation will finish within these three. But in reality, exactly getting 1.00, either plus or minus 1, exactly getting 0.00 is also not possible. Very rarely you get such correlations like perfect positive, perfect negative, and perfect no relationship. And sometimes somehow these two variables are related, and sometimes you get unwanted correlations, and these unwanted correlations are technically referred as spurious correlations. So sometimes you don't want a correlation, but you tend to get a correlation. So that's the idea. So be careful when you talk about a correlation coefficient. This is the idea, and it's the measure of dependency of one variable over the other. In that, the non-parametric form is Spearman's row, a measure of correlation used for the rank and ordinal data, where you rank them and use a formula 1 minus 6 sigma d squared divided by n into n minus 1. That formula you use and get a row. So that's called a Spearman's row. And whereas the Pearson's product moment correlation uses actual data, you should have what you call x and y, then you square each and x to get x square, you square each y to get y square, and multiply each x to y, xy. So you add another three columns, then use a formula. But now this is called as parametric form. Why? Because you're using it for a data which is quantitative in nature. Whereas Spearman's row, usually we say rank difference method, where you assign the ranks and then you go further for calculations. Now remember, before getting into the inferential statistics, you should be knowing something about the normal distribution of the data. So through descriptive statistics, you should be able to find out whether data is normal or non-normal. Because in a normal distribution, you are going to get a data set which is in the form of bell-shaped curve. I would try to show that. Okay, it's not there. Okay, you get a bell-shaped curve where 50% of the cases on the left side and 50% of the cases on the right side, and you have to check normality of your data. So once you're going to check your normality of the data, try to understand, please make a point where you're going to check your data normality through two of the tests. One is called as a Shapiro-Wilk test, SHAPIRO, Shapiro-Wilk test, and another one is Kolmogorov-Smirnov test. So I'll type that so it will be easier for you. So the test could be so one test could be you may be using Shapiro-Wilk test through softwares you can do. Otherwise, you can use Kolmogorov and Smirnov test for normality of your data. So these two tests will give you the idea of whether your data is following normality or not. Because in statistics, there is a rule. If your data doesn't follow normality, then you have to go for non-parametric tests, though your data is parametric. But if the data doesn't follow normality, switch over to non-parametric tests. So that's the idea. Then we'll move on to measures of relative positions, where it gives the idea of a participant's performance compared to the performance of all other participants. For example, if you go for CAT ranking, combined aptitude tests, there are several aptitude tests are done on the national level. There they give a what you call a rank. That rank is nothing but a relative position. They say what is your percentile, 90 or 85, because there's a cutoff is given, and that indicates the researcher to describe a participant performance compared to the performance of all other participants out of such 100 such people. So they are the measures of relative positions. One is percentile ranks, that's one thing, and there could be standard scores. So when you talk about a percentile scores, it indicates the percentage of scores that fall at or a given score. That's the idea. So even the percentile rank acts as a descriptive statistics. So usually in mathematical aptitude tests, in engineering tests and all, what they do is they don't rank simply. They rank out of 100 such people, where would be the person would be. So that is why they fix a cutoff. Okay, only those with 80 and above percentile can apply. That means what? Below of them are not eligible. And this can be done through statistics, and percentile ranks act as one of the descriptive statistics. Then we have a standard score, a measure of a relative position again. So what are those standard scores? The standard scores are at least three types. You have a Z score, you have a T score, you have a Stanine score, and a Sten score. So each one we'll see in next few minutes. So you have Z score, you have T score, and you have got Stanine and Sten. Now, Stanine means standard 9. Please make a note. Out of 9, you are scoring standard 9. Whereas 10 refers to standard 10. So that means what? All your scores are converted either into 9 or 10 scores. Then a norm will be fixed, and based on that norm, then you decide which is good. So we start with the what you call set.
Sir, excuse me.
Yeah.
Sir, your screen is not being shared.
Not shared?
No.
Wait a minute, wait a minute. Can you see now?
Sir, now it's okay.
Okay, so these are the 4 types of standard scores which usually employ in describing the data through descriptive statistics, called as Z score, T score, Stanine, and Sten. Stanine refers to standard 10, standard 9, and Sten scores refers to standard 10 scores. So how that will be? So we start with the Z score. So a Z score is a statistics, how far a score is from the mean in terms of standard deviation units. So how much, whether it's a +1 SD or whether it's a -1, is the distance between what you call a mean and a SD. So based on this, which is a statistics, it says the distance of a score, how far it is. So whether it's within +or -1, and this is required for making norms. Sometimes what you do in a few of the researchers, suppose you don't have established norms, what you do is you take mean and SD as what you call criteria points. You say mean +or -1 is average, mean +or -1 above is above average, mean ± below average is below. So what you do is you use them as what you call a distance expression, and this distance comes through the what you call SD value. So mean ± SD. So that is the idea behind a Z score. Then you have got a T score. A T score is nothing but a transformed Z score, because sometimes Z scores may be what you call little confusing. So what because there are minus scores also coming. So what you do is a transformed Z score, it avoids negative numbers and decimals by multiplying the Z score by 10 and adding 50. So many times while preparing a questionnaire and establishing a norm, what we do is we do this procedure. You what you call existing Z score is what you call multiplied by 10 and then add 50. So the idea is now it is converted into a T score. So a score of 50 represents the mean now. A difference of 10 from the mean indicates difference of 1 SD. Thus a score of 60 is 1 SD above the mean, while a score of 30 is 2 SD below the mean. So read more, you may be getting confusion. What is this Z score? But basically idea is multiply the Z score by 10 and add 50. You get a T score, and T scores can be furthermore easily interpreted. So that is the idea in the T score format. A few of the education people might do this for their establishment of norms. Then we go for stanines and standard tens. Okay, once we talk about standard score, it can divide a distribution into 9 parts. Then it's called as, it is standard 9. Sometimes we divide into 10, then it becomes sten score. So now you can see the picture, where in the picture is shown the different categories. So below 1% usually find 4%. They are called as lower categories. Then stanine 2 to what you call 3 called as below average. Then 4 to 6 are average. Then 7 to 8 is above average, and 9 is higher. And accordingly you can find what you call percent cases are falling, and 9 are distributed into only 5 categories up to 1, then 2 to 3, 4 to 6, then 7 to 8 and 9. So this 1, 2, 3, 4 categories have been divided, but again they are based on the percentiles. Sometimes what happens, same stanines are converted into stens, that means out of 10. So now 10 is referred as, up to 3 is considered as low, 4 to 7 are considered as average, and 8 to 10 are considered as high. So all this will give the idea of what you call how the scores have been transformed. So whether it's a standard 9 or whether it's a standard 10 or sten score or stanine score, the idea is you group the data in a descriptive way. So as I said, a stanine score can be any number between 1 to 9 in the case of stanine. In the case of sten, it is any score between 1 to 10. So a person said to be average if the score is 4 to 6. 7 to 8 are usually interpreted as above average, and anything 9 and above is called as high. So it's all given in a specific way. Whereas in the standard 10 or in the sten score, it is first cutoff is 3, second cutoff is 4 to 7, and the last cutoff is 8 to 10. So low, medium and high. So whatever it may be, these are the ways you can describe your data in different ways. Going back to our what you call original first level, what all we could do with the descriptive statistics are, you can see here. So where you can present your descriptive data, so statistics, in following ways, starting with the graphical representations and measures of central tendencies, measures of variabilities, measures of relationship, sten scores, stanine scores, T scores, and Z scores. All these through you can present your data in a descriptive way, which gives the picture of your sample in different ways, which describes your sample in different levels. So with this, we are going to finish the session, but we'll have few minutes left here. So any questions or clarifications, please feel free to ask under descriptive statistics. We are left with another 5 minutes. Usually 15 minutes to be given for discussion. I'm giving less.
Sir, good evening. Myself. So my question is, how to find out the correlation with the scatter plots? So how to find out the plots of scatter? So can you explain a little bit?
Okay, I'll go back to the scatter plot. Okay. Are you seeing the scatter plot now?
Yes, sir. Yes.
So now you see through scatter plot in Excel graph, in Excel sheet, you can derive this. Are you getting? You can derive
Yes, sir,
this, and you get a equation.
Yes, sir.
Y is equal to 3. In the present one, y is equal to the 3264x plus 5.7998. But down there is a r square. If you see,
Yes, sir.
and if you take the square root of it, you get a r. You get a correlation.
Ah. Yes, sir.
It's very simple.
So
Or
in
you
a
can.
actually, my question is, my doubt is, in a scatter plot is there is no plots are distributed somewhere in the top of the plots, red and
Okay.
blue. In there,
Here
when
there
you
are two
see-
variables. No, here there are two variables have been interpreted
yes,
on
that's
on the left one, and you get two separate equations.
okay. Okay.
See here I have on the lower side, on the right side down, I put only one variable. So that's why you have generated only one.
As
If I present two variables for scatter plot, it goes into different colors, and two separate what you call equations are generated, but you don't get a direct r, you get r square. You take
okay.
the root out of it, you get the correlation.
Okay, sir. Okay. Thank you, sir.
Okay, okay. More questions? But anyway, before winding up, again I request you to download SPSS evaluation version. Otherwise, our last session will be useless. Unless you work with me, it is of no use. So
Okay, sir.
please download SPSS evaluation version, any evaluation version, or if you already have SPSS, any version also will be fine. I'm going to introduce SPSS for you at least for 1 hour in the last session, because
Okay.
morning we'll be discussing inferential statistics.
Right, sir. Okay.